Okay, so we are continuing with our chapter summaries, perfect for a quick bit of revision, making sure you're ready to go and do some exam questions. And we are looking at what seems like a very simple topic, which is quadratics, pure year 1, chapter 2. Obviously comes up a lot in GCSE, but there are some new things here as well. So I want to start off talking to you about completing the square here. Now, what we're going to do is write the below in completed square form, and then afterwards we're going to state the maximum or minimum value of the function or the graph and the corresponding value of x that gives that maximum or minimum. So for this first one, it's a kind of U-shaped quadratic, this kind of shape. So we know it's going to be talking about a minimum, but I'm going to begin by putting this into completed square form. Now we know how to do this. We take this part and we half the size of it. So it's going to be an x plus 6 squared. We then subtract this thing squared. So I'm going to subtract 36. And we've still got that plus 10 that is there as well. So in completed square form, we have that y is equal to x plus 6 squared, and minus 36 plus 10 is minus 26. So if I go over here to try and answer the question to state the maximum or minimum value, well, our minimum value here, is this part. The minimum value is the second part that we've got there. The minimum value is 26. And this is when x is equal to, looking at this part, it's when x is equal to minus 6. Now, the reason it's the minimum value is because this whole thing here is something that is being squared. When something is being squared, the smallest thing it can be is 0. You can never get a negative because when you take any two numbers and multiply them, you get a positive unless the number you've taken is 0. So if this thing was 0, then this would be the smallest thing that we could have, hence it being the minimum. And when this thing is 0 is when x is minus 6. So we're now going to have a look at putting this second function that we've got here. This is our first introduction in A-level of function notation, of putting this in completed square form. Now, my tip for this is always just to factorize out the coefficient of the x squared, but I wouldn't do it for the whole thing. I would just do it for the first two terms, so that I have 2, let's zoom in a bit, brackets x plus 13 over 2. Oh, that's x squared, excuse me, like this. So I've just taken out a factor of 2 from these terms, so I have the 2x squared. Obviously, that would give me the 13x. And then what I'm going to do is I'm going to do the completed square form on just this part that's inside the brackets. So I have the 2, and then when I complete the square, I will have the x plus this 13 over 2. I will half that. That's the same pattern we do with completing the square. That will be 13 over 4 squared, and I subtract this thing all squared. Now 13 times 13 is 169, and 4 times 4 is 16. Close off the bracket, and I still have the minus 1 there. So when I expand this bracket, so I'm going to do this with this 2 with this, I get 2 brackets x plus 13 over 4, all squared. And rather than getting my calculator for this, if I'm going to do 2 multiplied by this, the denominator is going to get half the size when you double something. So I'm going to get minus 169 over 8, and I have minus 1. So my final version for this is that f of x is equal to 2 lots of x plus 13 over 4 squared. And you can do this on your calculator if you want to, but I'm just going to do minus, what would it be, 177 over 8 for that in completed square form. So again, it's a U-shaped quadratic that we have here because there's a positive coefficient. So we can now actually just go straight in and say that the minimum value is minus 177 over 8. And this occurs when x is equal to minus 13 over 4. Same logic as before. When this thing here is 0, when this bracket is 0, then this is the smallest thing that it can be. Because as soon as x goes away from minus 13 over 4, this is going to be a positive value. That means it goes away from that minimum value. I'm going to do one more example of completing the square. This time there's a negative coefficient for x squared. So I'm just going to take out the minus 3. So I have minus 3 brackets x squared. And this is going to be a 2 over 3 because I'm dividing by 3. And we just need to think, is it going to be a plus or a minus? It's going to be a plus, isn't it? Because we get the minus 3x squared. And then when these multiply, because I divided by minus 3, I get a plus here. And afterwards, I still have the plus 4 over 3. So just like before, I will complete the square on this inside bit. So I'm going to do the half of the 2/3, which is 1/3. And I'll subtract the 1/3 squared, which is 1/9. And I still have the 4/3. So now I'm going to do the minus 3 by this bracket and the minus 3 by the minus 9th. So I get minus 3 x plus 1/3 squared. And then there's a minus 3 times a minus a ninth, so that's going to be a plus 3/9 or plus 1/3. And we still have the plus 4/3. You notice how I didn't really do anything with the minus 1. I left it there as long as I could. Same with the 4/3 until this very last line of working where I can finish off with the simplifying so that I have 1/3 plus 4/3 is 5/3 like this. Now, because this is a this shape, like an n-shaped quadratic that we have, we're going to be looking at a maximum value. Okay, so this time we're going to say that the maximum value is 5/3, and this occurs when x is equal to minus 1/3, okay? It just happens that these have all got a plus. They don't have to have a plus. Obviously, there could be a minus in these bits, but just happens to be the questions that I've picked are like this. And again, it's because if x was any other kind of value, because it's being multiplied by a negative, it would take away from this 5/3, meaning that 5/3 is the maximum thing that it could be. And you can always put these on a graphics calculator or on Desmos, and it will help you visualize what is going on here. Okay, we're now going to have a look at solving equations, and there are 3 different techniques for this. There's really secretly a 4th one of using a calculator, but what I'm going to do is I'm going to do this next page here because I didn't want to waste our time on the quadratic formula. It feels very, very GCSE. So factorizing, again, that's one of our techniques for this. This is when you want to check to see, can you think of 2 things multiplied to this and add to this. I won't waste your time because this is very, very straightforward. We would have an a minus 5 and an a plus, oh my gosh, I almost did that wrong, and an a plus 3, because minus 5 plus 3 is minus 2, and minus 5 times 3 is minus 15, and that's equal to 0. This should feel incredibly familiar from GCSE. So we have that a is equal to 5, or a is equal to minus 3. We should never write and, because a cannot be equal to 5 and minus 3 at the same time. Now, we can use completing the square to find the solutions of something. And of course, you could do it on a calculator, but I wanted to show you this other technique. I'm also mentioning this idea of roots. Roots is saying when the equation that we're looking at, or when the function that we're looking at, is equal to 0. So we're looking at this function being equal to 0. Now, previously, when I had a coefficient for the x squared part, I factored it out like this because I didn't want to change anything about the function. I fundamentally wanted to keep that 2x squaredness about it. However, this is an equation. If I want to make this easier, I can divide everything by 2. Because 0 divided by 2 is still 0. So I get x squared minus 2x plus 1/2 is equal to 0. Now, you cannot divide everything by 2 in the previous examples because it would change what the function actually was. This one we are allowed to divide it because of the fact 0 divided by 2 is 0. We are actually allowed to do this. So now when I do completing the square, I will do half of that 2, which is a 1, and that's going to be squared. I will subtract this 1 being squared, or subtracting negative 1 being squared. I personally just ignore whether it's positive or negative. I just ignore that. I just subtract that number being squared. So I'm just going to be subtracting a 1 squared, which is a 1, and I have a plus 1/2. So I get my x minus 1 squared is equal to, I'll put the 1 on the other side and I'll subtract the half. 1 subtract a half is just a half. Now, all I need to do here is just square root both sides. So when I square root both sides, I will get x minus 1 equals plus or minus the square root of 1 over 2. Now, you can either put that in your calculator or do it manually. But when you put that on your calculator, the square root of 1 over 2 gives you root 2 over 2. So it's plus or minus root 2 over 2. So my final answer, when I add the 1 on, is that x is equal to 1 plus or minus the square root of 2 over 2. Okay, the quadratic formula, I'm going to just quickly put it in this box. Maybe you should see if you can remember it because we don't get given this. It is minus b plus or minus the square root of b squared minus 4ac all over 2a. And I've just done a very quick example here that you could try yourself. To solve this equation, you should come up with these 2 solutions for y. Y is equal to 3 plus or minus the square root of 13 over 2. And obviously, these are my values for a, b, and c that get substituted into that formula. Now, there is obviously an exam tip. Unless it is a show that question, you can simply just use your calculator to solve quadratic equations. So even here, you could have just put this into the equation. It would say 5 and minus 3, but if it was a show that question, you wanted to show all of the algebra, you could then just obviously, you know that those would be the brackets because you know that they would correspond to these answers. So you can be a bit sneaky in using your calculator. The second part of this that we've got here is where we're going to be doing pseudo quadratics. I call them pseudo quadratics. I know some other people call them quadratics in disguise that we've got here. So this first one that we're looking at kind of feels a bit like a quadratic, apart from we have a power of 4 here and a power of 2. Now, you might be able to recognize this straight away, but sometimes you can do a useful substitution for this. So what I'm going to do is I'm going to let y be equal to x squared, which means that y squared would be x squared squared, or x to the power of 4. So I have an x to the power of 4, so that's a y. I then have a 2x squared, well, that's a 2y. And I have a minus 35 equals 0. So I'm actually just going to use my calculator for this, okay? It doesn't say I need to show a full method, so I'm going to do my coefficients on my calculator. You shouldn't have to do this. Are 1, 2, and minus 35. So it tells me that y is equal to 5, or y is equal to minus 7. Now, it didn't ask for what y is. It actually wants us to solve it for x. So we need to go back to this part, and we just need to kind of substitute back in. So y is the same as x squared, so x squared is 5. And if I square root this, I get plus or minus the square root of 5. Now for this one, I get that x squared is equal to minus 7. And if you think to yourself, can you square a number and get negative 7? Well, we're talking about real numbers here, so if you do further maths, you know you could do it with an imaginary number. But no, we cannot do this. So this one has no real solutions. So our solutions for this equation are just that x is equal to root 5 or minus root 5. And again, this is another quadratic that is in disguise, but it's a little bit harder to see for this one. Now, I think the thing I'm going to use for my substitution is I'm going to say that y is equal to 2 to the power of x. And if I did y squared, well, that's 2 to the power of x squared. Remember, indices, you multiply these together, so it's 2 to the power of 2x. And now I can see that's going to be my y squared, and that's going to be my y. So I get 7y plus 2y squared minus 4 equals 0. If you want to, you can rewrite the order as 2y squared plus 7y minus 4 equals 0. And again, I'm just going to go straight into the calculator with my coefficients of 2, 7, and minus 4. It tells me that y is equal to a half, or y is equal to minus 4. But remember, y is 2 to the power of x. So 2 to the power of x is equal to a half, or 2 to the power of x is minus 4. Now, later on, you'll know how to solve this in a different way, but you should just be able to think to yourself, what does x have to be? 2 to the power of something that gives a half. It has to be minus 1. This one, 2 to the power of x to be equal to minus 4. There is no answer to this because an exponential graph, if you remember from GCSE, always is above the x-axis. See if I can draw it a little bit smoother like this. So there's never going to be a negative for negative 4. So this one has no real solution. So the only answer to that one is that x is equal to minus 1. Okay, then I want to talk to you about the discriminant. Okay, so I'm going to just quickly go to this little box that we've got over here, and we will discuss the discriminant. So the discriminant is one of the parts of the quadratic formula, and hopefully you're already thinking this yourself. It is b squared minus 4ac. So if the discriminant b squared minus 4ac is less than 0, this means that it's negative, and you're trying to take the square root of a negative in the quadratic formula in this part. So if this thing is less than 0, you're trying to do the square root of a negative. It doesn't have any solutions. So if the discriminant is less than 0, it means the equation has no real solutions, or no real roots. Let's do it as no real roots. And if it was a quadratic that we would be looking at on a diagram, it would be something like this, where it's not crossing the axis. If the discriminant is greater than 0, then the equation has two distinct, if I can spell properly, distinct roots. It's your classic kind of quadratic where it's crossing in two places. Here are the roots, here and here. And if b squared minus 4ac is exactly equal to 0, then the equation has something that we call a repeated root. The equation has a repeated root. And I'd hope you know what this is going to look like on a graph. I might need to use the power of Desmos to actually, not Desmos, of GoodNotes, to have it just touching it in one single place. A repeated root is where it just sort of skims the axis as a tangent. So for the discriminant, we've got this question here. It says, given that f of x has a repeated root, find the value of k. Okay, well, repeated root is this one that we've got down here. So we're going to say repeated root means b squared minus 4ac is equal to 0. So our value of a in this quadratic is k. It doesn't have to always be a number, it can be a letter. Our value of b is 5k, and our sort of value for c is 3. So b squared minus 4ac is equal to 0. So b squared, that's going to be a 5k squared minus a 4 multiplied by a multiplied by c. Let's zoom in on this. 5k squared, that's 5 squared and k squared, minus 12k equals 0. Now I'm going to factorize this so that I solve this properly, or I could put it on a calculator, I suppose, and I get 25k minus 12 like this, which tells me two things. Either k is equal to 0, or 25k minus 12 is equal to 0. So very easily you can put the 12 to the other side and divide by 25, and we get these values of k equals 0 or k equals 12 over 25. But I want to have a look at this, because it doesn't say find the values of k, it says find the value of k. So one of these is not going to be suitable. Let's have a look at k of 0. If k is 0, then we would get that f of x is equal to 0x squared plus 0x plus 3. So we've got the f of x is equal to 3, which as a graph is no longer a quadratic. It is literally just a line like this. And does that have any roots? Nope. It's not crossing the axis at all. So I'm going to reject that k is equal to 0, and I'm only going to accept that k is equal to 12 over 25, because if k is equal to 0, we get this strange situation over here where it's no longer a quadratic, and it also does not have a root. Okay, we're going to look at one more thing with the discriminant. It says prove that the curve with the equation y equals 3x squared plus c plus 6x plus c, where c is a real constant, has two distinct roots for all values of c. Okay, well, two distinct roots, we know that that is going to be when b squared minus 4ac is greater than 0. So let's have a look for our values that we've got here. Our a that we have is a 3. Our b that we have is a c plus 6, and a c that we have is a c that we have. A c, sorry. It's kind of confusing with the repeated letters, but don't let them kind of mix up, okay? So we're going to do our b squared minus 4ac. b squared minus 4ac is therefore equal to b squared, so that's c plus 6 squared minus 4 times a times c. So that is our c plus 6 squared minus 12c. Okay, let's keep working on this. C plus 6 squared, that's a c squared plus a 6c and a 6c plus 36 minus 12c. And then you can see what's going to happen here. This 6c and this 6c and this 12c all cancels out. So we get left with c squared plus 36. Now, because it's a prove that question, I think we need to explain something about this. So we can say, as c squared is greater than or equal to 0 for all c values, think of any number at all, whether it's positive, negative, or 0, it is always going to be 0 or greater. That's one of the key things about things being squared here. So as c squared is greater than or equal to 0 for all c, then we can say that c squared plus 36 is greater than 0 for all c values. In other words, we could say the minimum value of this is 36, and we said that if b squared minus 4ac is greater than 0, then there are two distinct roots. So as it's greater than 0 for all of c, then c squared plus 36 is greater than 0 for all c values. Hence, we do need a conclusion statement because it's a proof question. Hence, the discriminant is greater than 0 for all c values. So there are always two distinct roots. There are always two distinct roots. Okay, last one, modelling and problem solving. And I wanted to use this as an opportunity to talk about some general forms of quadratics, because I think it's something I could have improved in my playlist that we've got here. So just to quickly start off with, the most general form of quadratic you will see is like this. But if you were given the roots of an equation, then this could be a really useful one to use. You could say that b is to do with the root and c is to do with the root, but you put this extra a at the beginning of it because just because it's got two unique roots, it doesn't mean that it's actually going to be the only quadratic like that. So there's got to be this extra scaling at the beginning, kind of corresponding to this ax squared that we've got here. And then this one, if we know something about the turning point of the graph, this is a really useful one to use because we've got it in its completed square form and it's the generalized version of it. You might think, oh, I wouldn't use the a there, but you have to have the a in there to make it the general form of the quadratic. So this third form that we've got here is useful if you know something about a maximum or a minimum point that you've got. And you might have approached this question in a different way, but I thought I would show you my one for this. So it says a tennis ball is thrown from a point 1 meter above the ground. It reaches its maximum vertical height after traveling a horizontal distance of 5 meters. It is at a vertical height of 6 meters after traveling a horizontal distance of 9 meters. Given that its path is modeled as a quadratic function with vertical distance y meters and horizontal distance x meters, find y in terms of x, and then we'll have a look at the next part of the question afterwards. So it looks like what we've got, if I draw sort of very crude axes here, it's being thrown from a point. We know that it's going to be modeled like a quadratic kind of curve like this. Could probably make the ground a bit longer. And we're going to just add some things to the diagram. It says that a tennis ball is thrown from a point 1 meter above the ground. So I think this value here is a 1. It says it reaches its maximum vertical height after traveling a horizontal distance of 5 meters. So here's that maximum height that it's got. And it says that it has traveled a horizontal distance of 5 meters. And the last point it says is that it is a vertical height of 6 meters after traveling a horizontal distance of 9 meters. Okay, so somewhere over here where it's about 9 meters, doesn't matter how accurate that it is, I can see that it has got to a height of 6 meters. So if I was going to say that as a coordinate, this is 9, 6, and this coordinate we have here is 0, 1. Now we don't have anything about the roots for this question, and we could use this version of it as a quadratic, but because we're talking about a maximum point here, I think I'm going to use this general form of the quadratic that we have at the bottom. So I'm going to use my y equals a x minus b squared plus c. And so this is the general form I'm going to be using. Y equals a x minus something squared plus something else, okay? Now, I wonder if you can think about what this is going to be, where the turning point of the graph is. Now, the turning point is at 5 when x is 5. So I think this needs to be a 5 here so that we get a brackets x minus 5 squared. We don't know what this extra value is going to be because we don't know this maximum value. So I'm going to just give it a letter. I'm just going to call it c like we had in the previous part. So I've now dealt with this point. I've already used that one. I'm going to try and use this 9, 6 point next. So when x is equal to 9, y is equal to 6. So I get 6 is equal to a, 9 minus 5 squared plus c. So 9 minus 5, that's 4. 4 squared is 16. So I get 16a plus c. Okay, looks like I might be getting simultaneous equations here. And then when x is equal to, this is this next coordinate, because I've dealt with this one. When x is equal to 0, y is equal to 1. So using that top equation, 1 equals a, 0 minus 5 squared, plus c. So 1 is equal to 0 minus 5, that's minus 5. Minus 5 squared is 25. And I still have the plus c. So what I'm going to do is I'm going to take this equation, and I'm going to solve them simultaneously. Now, I know that comes up in the next chapter, but we should be able to solve these on our calculator very, very quickly with our two unknowns. I have 16a plus c is 6, 25a plus c is 1. And when this is solved on the calculator for me, it tells me that a is minus 5/9 and c is 134 over 9. So this means that our equation, using the one that we have at the top, is y equals minus 5/9 x minus 5 squared plus 134 over 9. And it shouldn't be surprising that A was negative, because the path of a tennis ball being thrown is going to be one of those upside down N-shaped quadratics that we've got there. And we can see that the maximum point is 134 over 9. This height is 134 over 9. What's that? 14.888 meters. And we can see that that turning point is when x is equal to 5. So it now just wants us, for the next part of the question, to work out the horizontal distance it has travelled when it reaches the ground. When it reaches the ground is when y is 0. So when y equals 0, we get that 0 is equal to minus 5/9 x minus 5 squared plus 134 over 9. And we're just going to solve this equation, which should be pretty easy. I'll put the 5/9 x minus 5 squared over here is equal to 134 over 9. I can cancel out 9s by multiplying both sides by 9. I am then going to divide by 5, so I'll have 134 over 5. And so if I square root both sides, I get that x minus 5 is equal to plus or minus the square root of 134 over 5. And so x is equal to 5 plus or minus the square root of 134 over 5. Now, there's not much point in doing 5 minus the square root of 134 over 5, because it's actually going to correspond to the bit on the graph where the ball has kind of come backwards, and it's corresponding to this bit. So we won't be using that one. We'll just do the other one. So on my calculator, I'll do 134 over 5. I'll square root that answer, and I will add 5 to it. And we get... if I've done it incorrectly, I don't know if I did type that in correctly, 134 over 5, square root the answer, plus 5, and we get 10.18 meters, I believe. So x is equal to 10.18 meters, and I've done that to 2 decimal places. And they could probably ask you something about modelling assumptions with this. So that's pretty much everything I think that they can ask you about with quadratics. Obviously, this is going to get harder with these different ones as we go through the chapters. I try to cover as much as I can. Hopefully, this is the kind of video you'd like. If you want something to be shorter, longer, what kind of thing that you'd find interesting, I'm always open to feedback as I go through these playlists that I'm making. Good luck with your revision, and I'll see you in another video soon.